So let us start with a new chapter called Photoelectric Effect. When UV rays fall on the negative plate, which is also known as the anode, immediately current flows in the circuit, and as soon as UV rays are stopped, the current also stops. But on the other hand, if UV rays are made to fall on the positive plate, which is the cathode, then no current flows. So the reason why current flows when UV rays hit the negative plate is when UV rays fall on the negative plate, electrons are released. And these electrons are then attracted by the positive plate. So electrons move from anode to cathode. So electricity flows from positive terminal to negative terminal. Now the reason behind this experiment, or the conclusion which we can draw from this experiment, is that when light ray or UV rays fall, then electrons are released. This is the fundamental foundation on which photoelectricity is based. So now what is photoelectric effect? The phenomenon of emission of electrons from metals under the effect of light is called photoelectric effect. So here we are talking about metals. It can be from the surface of metals or from the interior of metals. Now there are Hertz and Lennartz, and they performed various experiments, and from the experiments we can get some conclusions which we have to study. So the first conclusion we got was dependence of intensity of light. So the emission of photoelectrons is directly proportional to the intensity of light. So if we plot a graph with photoelectric effect on the y-axis and intensity on the x-axis, then we get a straight line. So from this we can say that it is directly proportional. Next we go on to the effect of potential. So with increase in potential, current initially increases and reaches a maximum and then becomes constant. So we can see from this graph that, let us consider intensity I. So current is increasing and then it becomes a constant here. And if we consider another one of 2I, then it also increases and becomes a constant. So at a certain level it is becoming a constant. Now, so basically this curve explains that when intensity is doubled, the value of current is also doubled. So the negative potential at which photoelectric current becomes zero is called stopping potential or cutoff potential. So from this graph, we can see that at a point V0, the value of I is 0, but potential is at a negative value. So at this negative potential, the current is becoming 0, and this potential is known as cutoff potential or stopping potential. From here we have a formula which is Ek equals EV0. Ek is the maximum kinetic energy. E is the charge on one electron, and V0 is the stopping potential as we discussed here. So from here we can conclude that the maximum kinetic energy is independent of intensity of light. Now we go on to the third factor, which is the frequency. So when we consider this graph of potential difference versus current, we consider the intensity of light to be constant and the frequencies are different for different radiations. So the saturation current is same. So V01 and V02 are the stopping potentials of, suppose, V1 and V2. But after a certain point, they are achieving a same value of current. So the saturation current is same. but the stopping potential is different. Another conclusion we can draw is when the frequency is higher, then the stopping potential will also be higher. So the maximum kinetic energy will also be higher. So maximum kinetic energy variation with frequency of incident light. So it varies linearly. So in the x-axis we plot the frequency v, and in the y-axis the maximum kinetic energy. So we get a straight line, and at a point when the maximum kinetic energy is 0, v naught. From this graph we can say that Ek equals AV minus B. So it is in the form of y equals mx plus c. So y is Ek, m is the slope which we know is A, x is V, and c is minus B. So next, from this equation Ek equals AV minus B, we can say that from the graph, if V is equal to V naught, so V, frequency is V naught, then the value of Ek is 0. From here we can go on to this part, where if from the equation Ek equals AV minus B, Ek is 0 when V is V naught. So 0 is equal to AV naught minus B. So B is AV naught. B is the minimum energy for emission. The minimum energy we require for the emission of photoelectrons is also known as work function. So in case you are asked about the definition of work function, it is the minimum energy required for emission of photoelectrons from a metal. Next we go on to threshold frequency. The lowest frequency of light which can emit photoelectrons from a material is known as threshold frequency. Below this, no photoelectrons are emitted. So here the lowest frequency, so for this curve V02 is the threshold frequency, for this curve V01 is the threshold frequency, and for this curve V0 is the threshold frequency. V0 is the threshold frequency and not the stopping potential. Potential is capital V, and frequency is small v. Now we go on to the 5 laws of photoelectric effect. The first law is that the rate of emission of photoelectrons from the surface of a metal varies directly with the intensity of light. So this is what we already studied, where we saw the graph which is a straight line like this. So the next law is the maximum kinetic energy of emitted photoelectrons is independent of the intensity of incident light. We saw the equation Ek is EV naught. So here we have no relation of intensity of light. That is what the second law states. The third law is that the maximum kinetic energy of photoelectrons increases linearly with the increase of frequency of incident light. So we saw that from this graph that it increases linearly. The fourth law is that if the frequency of light is below a certain frequency, then no photoelectrons are emitted. This frequency is known as the threshold frequency and is different for different metals. Right, we saw photoelectric in the maximum kinetic energy versus frequency curve. We saw that at a point where the maximum kinetic energy is 0, that point is known as the threshold frequency. And the fifth law is that as soon as light is incident, photoelectrons are released instantly. So suppose this is the surface. As soon as the light touches the surface, electrons are emitted. Now, we had earlier studied about the wave theory. So this photoelectric effect goes against the wave theory. We are going to study 3 ways in which it goes against the wave theory. So the first statement is, according to wave theory, light strikes the surface and energy is distributed uniformly to the electrons on the surface before electrons are emitted. So as light intensity increases, energy also increases, right? So the light strikes the surface and it gets evenly distributed in the surface, and after that electrons are emitted. So we can say if more light intensity is struck against the surface, then there is more energy distribution. But experimentally we proved that maximum kinetic energy is independent of light intensity, right, from the equation Ek equal to EV naught. So this is the first point. The second point is, according to wave theory, light of any frequency should be capable of ejecting electrons from the surface. But experimentally we found that light of frequency less than threshold frequency cannot eject electrons. And the third statement is, according to wave theory, energy from light is distributed evenly throughout all electrons, right? So here distributed uniformly, evenly through all electrons. So by the time it reaches the surface and it distributes itself uniformly, we will see that some time lag is there. But we saw the law of photoelectric effect that there is no time lag. So third statement is also against the wave theory. Now we go to Planck's photon hypothesis. For this we will need to know what black body radiation is. So a black body radiation is the spectrum of light radiated by any heated object. And all the radiations can have wavelengths varying from 0 to infinity. So at a particular temperature, radiant energy is distributed among different wavelengths, right? But no scientist could express the distribution of radiant energy. So all the scientists knew that the radiant energy is being distributed through all the radiations of wavelength 0 to infinity. But the expression which mathematically expresses the distribution was not yet clear to them. So what Planck said is that the emission of radiation is not continuous. In fact, it happens in small bundles or packets, and these small bundles or packets in which energy is released are known as quanta or photons. So energy is not directly emitted, it is emitted in small bundles or packets which were known as quanta, and then the name was changed to photons. So the energy associated with each of these packets, which are quantum or photon, is hv. So energy is equal to hv according to Planck's hypothesis, where h is Planck's constant. Planck's constant has a value of 6.6 into 10 power minus 34 joule second. And v is the frequency of radiation. So energy may be released as hv or 2hv or 3hv, all integral hvs, but not anything in between, no fractional parts. So here is a small numerical. Wavelength of some visible light radiation is 5000 angstrom. Find the frequency of the radiation and the energy of each bundle or photon of this radiation. So firstly, frequency. We know C is equal to V lambda. So we can say that V equals C by lambda, and C is the velocity of light, which is 3 into 10 power 8. Lambda is 5000 angstrom, which is 5000 into 10 power minus 10 meters. So V is equal to, by mathematically calculating, it comes out to 6 into 10 power 14 per second inverse. So as energy in each bundle is hv, from the formula we derived earlier. So H is 6.6 into 10 power minus 34 joules second into V, which we've calculated earlier, and we get the resultant energy, which is 4 into 10 power minus 19 joule. Next we go on to Einstein's explanation on the basis of Planck's theory. So Planck's theory is that light travels in small bundles known as photons of energy or quantum. The energy of each photon is hv, where v is frequency and h is universal Planck's constant. And the intensity of light depends on the number of photons, right? So according to the Planck's hypothesis, a photon falls on electron and the energy is transferred to the electron. So the entire energy of the photon is instantly transferred to the electron. And after the energy is transformed, photon is just energy, and when it has no energy, we can say it vanishes. And part of the photon's energy, which is transferred to the electron, is used by it for ejection from the surface. So electron uses part of the energy to escape from the surface. And the remaining energy is stored in the electron as kinetic energy, maximum EK. Now some electrons are ejected from the interior of the metal. It is not from the surface but interior, from the interior of the metal. So along with these energies, firstly it uses the energy from photon on collision with other atoms during journey from interior to surface, right? From the interior it has to reach the surface, but on the way there are other atoms, so it has to collide with all the atoms and then escape, and collision leads to it losing some energy. Thus, electrons with different energies are emitted from the metal, right? Some are from one level of the interior, and some are supposed from even deeper interior, and some are from the surface. So all these, when being ejected from the surface, will have different energies, right? So kinetic energy of surface electrons is greater than kinetic energy of interior electrons, because it does not lose energy during collisions. Now let us go to some mathematical derivation of Einstein's equation related to Planck's hypothesis. So firstly we know hv is equal to the energy, that is equal to W plus EK. EK is the kinetic energy and W is the work function, which is the minimum energy which is required by the electron to be ejected from the surface. So from this we change EK to this side and we bring HV to that side. EK equals HV minus W. Suppose energy which is absorbed is less than the work function. So then we can say that electron will not be emitted. W has to be equal to HV naught minimum, where V naught is the threshold frequency and H is the Planck's constant. Now we substitute W equals HV naught in equation 1. So we get EK equals to HV minus HV naught. Taking H common, we get H into V minus V naught. Now we know kinetic energy is equal to half mv square. But this is the maximum kinetic energy, so it will be half mv max square because mass will not be changing. Velocity will be the maximum at one point. So half mv max square is equal to EK, which is equal to HV minus V naught, which is equal to H C by lambda minus C by lambda naught. Because C is V lambda, so V will be C by lambda. So from here we can get another formula, which is half mv max square is equal to hc into 1 by lambda minus 1 by lambda naught. And these are the formulas, the 4 formulas which you have to remember. Now we also know that photoelectric current small I is directly proportional to the intensity of light I. So we also get a linear graph here. So So we know half mv max whole square is equal to hv minus v naught. So at stopping potential, the maximum energy electrons are stopped. So all the kinetic energy, half mv square v max whole square is equal to ev naught, right? Ek equals ev naught. So from 1 and 2 we can say that hv minus v naught is equal to ev naught. But remember, this is a capital V because this is potential, capital V, and small v is frequency. So v naught is equal to h by ev minus h by ev naught, and h by e will be the slope. So we know Einstein's equation, which is E equal to mc square, and Planck's equation E equals hv. So we can say that mc square is equal to hv. Moving c square to that side, we get hv by c squares, and m is the kinetic mass. So m equals hc by c square into lambda, because we substitute v by c by lambda. So we get h by c lambda. So the kinetic mass can be expressed as hv by c square or h by c lambda. Momentum is, as we know, mass into velocity, and we derive mass equals hv by c square. So hv by c square into c. C gets cancelled, we get hv by c. Again we know v equals c by lambda. So momentum is h by c into c by lambda. C gets cancelled, so we get h by lambda. So momentum can be expressed as hv by c, e by c, or h by lambda. So that is all about photoelectric effect. Thank you for watching.